Hi and hello once again. So we are now on problem number 8 on lesson number 6, transmission and distribution under the power transmission and distribution subject in terms of, I think, performance of the line. So before we go with anything else, I want to thank you all subscribers, and as of the moment we have 1,240 subscribers. Thank you very much for all the love and support. So I will try my best to discuss more relevant content in terms of refreshers and some of the reviews and some retro gaming on our OERT channel, or the Online Electrical Engineering Review and Tutorial channel. Okay, now let us have problem number 8, but before we discuss the solution, let us read the problem first. A 3-phase 50 Hertz overhead transmission line 100 km long has the following RLC constant. R is 0.1 ohms, reactance is 0.2 ohms, susceptance 0.04 times the negative 4 mhos, and our main goal here is to determine the transmission efficiency when supplying a balanced load of 10,000 kilowatt at 66 kilovolt at a power factor 0.8 lagging, and we will use a specific line, no? In this case a medium line, which is a nominal T approximate. Okay, before anything else, let us have the given first. So from what we have already read on the problem, our power factor is 0.8 lagging. The PR is 10,000 kilowatt, or simply in terms of megawatt, we have 10 megawatts here. And our VR is 66 kilovolt. Okay, now we need to do first the circuitry, because on the circuitry it's very important, because we can derive some of the important formulas that we can use in the solution. Now this is a nominal T approximate, as you can see here. Okay, we already describe or discuss this transmission line on the basic fundamentals, so go back again to the basic fundamentals, but we need to repeat it again so that we can see the relevant equations. Okay, now in this case, this is not letter A, but we have only transmission efficiency that we need to solve. Okay, now you have here nominal T. The description here is you need to have distributed parameters here, and please take note the ZL here is simply your R and your JXL, and must be divided by 2. And that is ZL all over 2. Okay, now for this, it is distributed at the sending end and the receiving end. Okay, and that's why it is called nominal T, and you have a lamp parameter here, which is your C. And definitely your C here, if you can still recall, is 2 pi FC, which is definitely your susceptance. Considering in a medium line, the conductance is negligible. Okay, now in this case your C parameter is lamp at the midpoint. You have your currents IS, IR, and IC here. Is definitely, if you use a little bit of KCL, we can have these equations again. Okay, your IS here simply equal to IC plus whatever your load current, which is IR. Another equation that we can develop here is definitely we can have this equation here, which is you can get the parameter of your voltage at the capacitance or your capacitive voltage here at the midpoint by using a little bit of KVL, a little bit of circuits. VRN plus the drop IR multiplied by ZL over 2, which is this one. Okay, so that we can have this relationship. Another relationship that you need to know is the voltage at the sending end. Definitely, and we need to have that in order to get the parameters at the sending end. And it's pretty clear. I can have here, if we get VSN, okay, the parameter VSN is VCN VSN is equal to VCN plus the drop here, definitely that is IS times ZL over 2. So, IS ZL all over 2. Okay, we'll make use of this one on the next slide. So, in this case, we just get first IC so that we can get IS. After get your IS, you can now get your VSN. Okay, so those are the main equations here, as you can see, no? So your IS, IC plus IR, your VCN, and your VSN respectively. Okay, let us move on. Let us have the parameters. So the length of the line is 100 kilometers. So if we multiply 0.1 by 100, therefore, we can have in ohmic value, we have 10 for the resistance per phase. The reactance per phase, 0.2 times 100, you have J20. And then you have admittance, which is admittance per phase is 0.04 times 10 negative 4 times 100. We have 4 times 10 negative 4 mhos. And we need to get the VRN here, since the system is balanced, you need to divide it by square root of 3, definitely. So you have 66K all over square root of 3 bar 0, which is our reference, definitely our reference. Okay, sorry. Reference or default is the receiving end voltage. So you have 38.1 kilovolt. Okay, now we need to get the load current. So please take note, since we are given with a PR, therefore you need to have your power factor, the receiving end must be divided. So if that is SR, please take note there's no PFR. Okay, now this we already discussed this many times. So that is PR over square root of 3 VR PFR. So please take note this 10 megawatt. VR, we have 66K. Your power factor is 0.8, right? So to get the angle, so using your your CSQ table, we have here a negative, which means that is a lagging condition. Okay, the lagging condition, we have the inverse of that power factor. Okay, in this case, we can now get the angle because power factor is cosine of the angle theta. So we need to get that theta to have the direction part. Okay, the answer is 109.34 bar negative 36.7. As we have discussed, we need to get VCN first so that we can get IC. So for that, VCN is VRN plus IR ZL all over 2. All of the parameters already given. So VRN is 38.105 kilo bar 0 plus 109.34 bar negative 36.7. Please take note, you have your ZL, 10 plus J20, and don't forget to divide it by 2. The answer is VCN with the angle of theta 1 for that for the direction part, 39.20.24 bar 0.7999 kilovolt. And thus, from our equation, that we discussed in terms of the IC, the capacitive current, okay, we have JY-VCN. So VCN, please take note, this is a phasor. And don't worry about the Y, we already have the J there, the parameter there for the direction part. So we have this J, 4 times the negative 4, and then 39.2024 bar 0.799 kilo. And thus, the answer I here is, for the charging current, or your IC, is 15.6809 bar 90.799 degree ampere. Okay, now we need to discuss the next part for getting your transmission efficiency. See you. Okay, so let us conclude our not last problem, problem number 8, so that we can move on to the next few problems. So as we have recalled from our last slide, that we can get your IS by adding IC and IR. Since IC and IR are already computed, so we can get IS here simply 15.6809 bar 90.799 plus your IR 109.3466 bar 36.87. If you add it vectorially, the answer is 100.53 bar negative 29.78 degree amperes. Okay, so another recall that we already have established this equation from the circuitry So we can now get VSN bar alpha. Alpha is the transmission angle. Okay, that's the difference between the angles of your reference and your sending end. So we have VCN plus IS, then multiply by ZL over 2. Since, okay, this is kilo. I forgot to mention this is kilo. So you have 39.2024 kilo bar 0.799 because this is kilovolt. Then plus 100.53 bar negative 29.78 multiplied by 10 plus J20 all over 2. Now, if we do that, we can have this answer here for the VSN bar alpha as 40.1519 bar 1.699 kilovolt. So we need to get this alpha here and this angle here, I could say theta I, so that we can get the power factor. Okay? Now in this case, pretty clear to get the power factor, which is cosine of theta S, which is the angle difference between the voltage and the current. Please take note, this is theta V minus theta I. Okay, the theta V here is definitely your alpha, and your theta I is your 29.78, which is computed recently. So we have 1.669 minus negative 29.78. And thus, if you do a little bit of your math here, the answer is 0.853. Now, it will become lagging because your theta is positive. But if this theta is negative, definitely the angle is in a leading condition. So you can use the free body diagram if you want, but again, by analysis, we already have this one in terms of the angle. If that is positive, that is in terms of lagging condition. Okay, now, in this case, how can you get the efficiency? The efficiency is simply P out over P in, which is PR over PS times 100%. Now, your total efficiency now, it can be, okay, in terms of line value or in terms of per phase value. Well, I do this in a per phase basis, but the answer is still the same. It will cancel the 3 here, and then you have VRN IRPFR, VSN ISPFS times 100%. So just have all of the computed value, but this is given 38.105 kilo times 109.3466 times 0.8, and then 40.159 kilo times 100.53 times 0.853. Okay, doing the math here, you have 96.81%. Okay, so this is the typical solution. However, you can have another alternative in terms of P losses. You can have the efficiency in terms of P out all over P out plus P losses. And then you multiply it by 100%. This is an alternative. But here in a nominal pi, you have 2 losses. Please take note. You have the losses on the sending end and you have the losses at the receiving end. And then if you get those losses by having 3I squared R, right? Then please take note, the R must be divided by 2. You need to add those 2 losses and then the P out, and then you divide it by P out. So you can do the same thing. The answer is still the same. That's an alternative way. Okay? But I establish here this solution here so that we can solve all of the important parameters. The sending end current, the sending end voltage, the sending end power factor, and then the efficiency. In other words, you're hitting 3 birds in 1 stone. Okay, let us move forward to problem number 9. See you.